Okay. Now, so far, and I'll have to repeat a few things now. When we talk about the evolution of what we know as the atomic models, we have covered, of course, the Thomson plum pudding, model, the Rutherford shell model, in our last lecture. Now we want to look at the evolution of how Niels Bohr came up with the concentric ring model. And from some of the conclusions that Niels Bohr presented in his concentric ring model, we evolve into the modern quantum model, or the Schrodinger quantum model. So we have those two completed. Now we wish to look at these two in today's lecture. The simplicity of the Bohr concentric ring model is based upon what we call the understanding of the bright line spectra of atomic structure that is emitted from atomic structure. The handout that I gave you shows some atomic structure, some bright line spectra that's evolved or observed when we study bright line spectra of certain elements. So in this graphic here, you of course see the top is the continuous spectrum, is all wavelengths in the visible spectrum. I think I gave you a handout last time that showed all of the types of wavelengths in the electromagnetic spectrum. And we find that the continuous spectrum is a very small window of that larger wavelengths or types of electromagnetic radiation, and we see it running from 4,000 to about 8,000 angstroms in this, or 400 nanometers to about 800 nanometers. And we'll talk about nanometers and the units that are used in wavelengths in just a few minutes. But when an element, pure element, is put into a confined space or a glass tube, for example, and an electric current is passed through it, it will have a, what they call a net color to it. It will have an overall glow, and that glowing color is sent through a prism. It breaks up into what we call the bright line spectrum of the elements. Each element has its own pattern. Here is sodium. All sodium elements will demonstrate this kind of pattern if you run the light through what is called a spectroscope. Very simple instrument. It's just a mounted prism with a little telescope on it, and you can see the colors that are generated. I'll show you that in a minute. Hydrogen here is the one we're fixing to spend most of our time on, and you see 1, 2, 3, 4 colors that are typically generated from the hydrogen atom. So, and then you have calcium and mercury, just to show you a couple more examples. But every element has its own bright line spectrum. Now, the hydrogen spectrum, just as a point of issue, is like all hydrogens have this spectrum. So how did they learn what the composition of the sun was? And when they ran the sunlight through a spectroscope, long story short and simplified, this is what they saw, a hydrogen spectrum. And so one thing led to the next, and they came up with the energy source that exists in the sun. Now, the one we're going to be focusing on, of course, will be the hydrogen spectrum. To generate a bright line spectrum, a sample of gas of interest is placed into a glass tube and attached to some electrodes, and these electrodes send an electric charge through the atoms. Now, when that electric charge goes through, the atoms undergo what they call go to an excited state. So when you apply heat, light, and electricity to elements, the electrons absorb that energy and jump up and down. It's kind of like, like a bunch of ping pong balls in a lottery globe. Anyway, when they jump up and down, they go up, absorb energy, and then they fall back down toward the nucleus and give off the energy. And all of the electrons bouncing around together give a specific color. Well, that specific color goes through a slit, which is sent through, this is a, I don't know what, they don't have anything on that. Sometimes they use a diffraction grating, which is a piece of glass with 30,000 scratches per inch. But here they're showing a prism, just like you would have crystal light passing through a crystal chandelier. You would see the rainbows generated on the walls around the dining room, if you so forth. But as it goes through, you see that this is broken up into the 4 spectral colors that are associated with the hydrogen. The shell model, which was proposed by Ernest Rutherford, as you recall, is a nucleus surrounded by an electron cloud. But because of the transitions, these are transitions, electron transitions, that's what the lines are generated by. Electrons going up from the nucleus and falling back down, they give off energy. Okay? And some of them give red light, some give green light, some purple, and some violet, blue and violet. So Niels Bohr and his group came up with the idea, says, well, electrons are not just moving around in random patterns. They exist within certain quantum levels, is what his reference is. And these quantum levels are the rings that surround the nucleus, much like, and they visualize the rings and the electrons running around the nucleus, much like planets run around the sun. So in a simplified format, you visualize, of course, it going all the way around. These represent what they call energy levels. And we have electrons in that particular energy level, We call that energy level, and they're designated by the lowercase n symbol. That's n equal 1. So that's the first ring, called the first principal energy level. And then we'll have an n equal 2, n equal 3, and go on out to n equal 4, n equal 5, n equal 6, n equal 7. Now the reason I stop at 7, if you count the rows on the periodic table, that's the maximum number of rings that we have knowledge of in the community, in the scientific community. 1, 2, 3, 4, 5, 6, 7. So we're going to get into something called the building process, taking electrons and putting them in the right place around the nucleus. It's called the building up process. Well, if we're talking about electrons in the first energy level, we're talking about like the hydrogen, helium, they only have one ring around them. Well, when you go to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, those elements have 2 rings around them. And then the third row, all elements there have 3 rings. And then you get down to the fourth row, all have 4 rings. Now you'll notice that the number of elements increases when you get down to the 4th level. So some of the electrons are being placed in other rings, and I'll show you why that occurs in just a moment. But you can count all the way up to 7 here. Now notice how, if you recall, when we studied the lanthanide or the lanthanide-actinide rare earths, they go into this position right here, and this is separated from the table for convenience more than anything. But these two are part of 6 and 7, rows 6 and 7. So the lanthanides would have 6 rings, along with what are the others up in the chart, and the actinides 7 rings around them. There is a simple formula for defining the maximum number of electrons that a principal energy level will have, and that is max number electrons is equal to 2n squared. Very simple formula. That is, if you want to know the maximum number of electrons that can be placed in the first energy level, you place a 1 there and square it times 2. So we can put 2 maximum electrons in that first ring. Once that is full, so to speak, we have to go to the n equal 2. And the n equal 2 would be 2 times 2 squared, which would be 8. So this second ring would have 8 electrons. And you continue on out. And so 3 squared, 3 and 3 is 9, 2 9 is 18. You can have 18 electrons. And 4, 4 is 16, 72, 4, 4 is 16, 64. Change that to 32. Okay, 5 and 5, 25, 2 down, so 25 is 50 for this third one. You don't have to memorize these. This is what you need. And of course, a simple question on the exam will be given the 5th energy level, how many maximum number of electrons can you put in that ring? So now you can calculate that. 36, and that's 72, and then 49, 98. So you can see that there's plenty of room as you move along in the periodic table. Now, in the filling up process, we can have rings that this is the maximum number that you put in, but that doesn't mean a given element has that number of electrons. It just means that that is the room it has for electrons. Okay, now we have a nucleus, say, down here. And the first energy level, n equals 1, is right here. Then n equal 2 is quite a ways from that. Now you'll see this evolve as a logarithmic arrangement. And what I'm doing is just taking kind of a fragment, slice out of the atom. And it would go all the way around in a circle, of course, giving the concentric ring sequence. Now as you go up a little higher, these begin to converge, n equal 3. And then n equal 4, then n equal 5, n equal 6, and n equal 7. Now, when an electron will start in the second energy level. And so there is an electron right here. Now, when that electron is when everything else is full, so you've got 2 electrons in this one and we've got 1 electron in the second one. You can't put any more here, so you have to put any future electrons in the second energy level. So this 1, 2, 3 electrons, so that hydrogen lithium. Now listen to this. This is an important term. When all of the electrons for a given element are placed in the lowest available energy levels, it's called the ground state. So with the electrons in the first ring, 2 in the first ring and 1 in the second ring, lithium would be in its ground state. Now, if this lithium was placed in a discharge tube like that and electricity sent through it, the electrons are going to absorb energy. So energy comes in, and we'll just take this 1 electron right here. It's endothermic, and what happens, this absorbs that energy, and when it absorbs it, it jumps out to a higher level, and that's called an excited state. So excited state of the electron configuration. So when we turn the electricity on to the hydrogen, and hydrogen, you know, it only has 1 electron in 1 ring. Well, that hydrogen absorbs energy and jumps out to a higher level and then falls back down to wherever it's going. Now the fall may go down to, if it's a first level electron going out, it might fall back to 1. We're talking about the second level electron. Well, it goes out somewhere, we don't know where, and falls back to number 2. Or it goes out and goes out to 6 and falls back to 2. Goes out to 2, 3, 4, 5. Goes out to 5 and drops back to 2. And goes out to 4 and drops back to 2, or jumps out to 3 and drops back. Like that. So when you hit these electrons with electricity, you don't know where they're going. They just absorb and just jump out to a higher level. But when they fall back down, that's when you see them. Now, we can't see the 7 to 2 transition. Oh, let me make a statement here. The reason I'm using the n equal 2 as the floor of the return is that's where all visible transitions end. So everything that ends on n equal 2 is a visible transition. Visible spectrum. And you can see this. These are the bright lines we showed you at the beginning of class. And the n equal 3, if anything transitions out and drops back to n equal 3, it's called the infrared, IR spectrum. And you have to have special spectroscopy equipment to see those transitions. And if it falls back to number 1, it's a UV transition, UV spectrum. The energy's too high to see. So the reason I'm ending all our transitions on 2 is because we can see them. Okay? Now, the 7 to 2 transition, we can't see, and it's still part of the visible, but the wavelength is so short and the energy is so high, this is borderline UV visible, not seen with the naked eye, so to speak. However, if you have a transition from 6 to 5, 6 to 2, 5 to 2, 4 to 2, 3 to 2, you're going to have colors coming out of those spectrum, those transitions. The longest transitions are the purple end of this. So a 6 to 2 transition gives a violet color. A 5 to 2 transition, that would be this next one, gives a green color. You look on your handout that I gave you down there at the bottom, and you can see these colors. There's a green transition. And if we have a transition from 4 to 2, now wait a minute, I'll take that back. The 5 to 2 is a blue transition, I should say, and the next one's a green. My bad. Blue light. Now, I'm sorry, this should have been a blue one. Then we have the green for the 4 to 2 transition. And then from n equal 3 to 2 is the red band. Now, this is still in hypothesis mode for the Bohr model. So in these transitions, we have the red line, green line, which you'll see kind of off in a distance like that. Now, blue line, like that, and a little closer in, that violet line. Now again, there is one out here that's a 7 to 2 transition, but you can't see that one. It's just is invisible to the naked eye. Now, in studying these, there are certain things that you have to understand. What you're looking at here is electromagnetic radiation, light. So we need to evaluate these spectra in terms of light or electromagnetic variables. Okay. So there are two topics that we need to look at. One is the wave equations for electromagnetic radiation. And they're very simple to use. Light is electromagnetic radiation. Now, the wave variables include wavelength, frequency, and energy primarily. Now, there is a variable known as amplitude, which is simply the height of the wave, but that is not taken into account in the equations I'm about to show you. But wavelength is given by a symbol lambda. I'll explain these in detail. Frequency, you'll find, looks like a V, or you might in some cases see a lowercase script f for frequency. And of course, energy is simply delta E for whatever wavelength you're talking about. Now, to understand these, you have to understand the relationships between these variables. In light, being electromagnetic radiation, travels through space in what we call energy packets called photons. Energy packs. And so energy packs have a wavelength, a frequency, and an energy. And it's kind of like, well, we got a bunch of electrons, okay? They have a certain character to them, and we'll look at that eventually. But these are like, I think of them mentally as raindrops, and then different color raindrops. But the wave is typically described in terms of the sine wave. And for one cycle, from start to finish of one wavelength, is the sine wave, where it starts at 0 and goes to 2 pi, if you're familiar with that. So this is one wavelength. Now, frequency simply is the vibration rate. How fast it oscillates in its static position. So just up and down oscillation. Now, the relationship between frequency and wavelength for electromagnetic, well, for any waves, that matter, is inversely proportional. That is, frequency of vibration is proportional to 1 over the wavelength. That is, if you have long wavelengths like this, and then they start getting shorter and shorter and shorter, like this, these waves down in here will be at low frequency. Long wavelengths. These would be high frequencies, short wavelengths. So we have a relationship that's inverse when we talk about propagation and movement of the waves. Now, there is one more wave variable I haven't brought in there, and that's the speed of the wave. Well, since we're talking about electromagnetic radiation, the only thing you need is the speed of electromagnetic in a vacuum, the speed of light in a vacuum. And the speed of light in a vacuum is, and you've heard of 186,000 miles per second. Well, in the work we're going to be doing, we need it in meters per second, and there's 3 times 10 to the 8th meters per second. And that's swift. You can convert 186,000 miles per second to meters per second if you wish to prove it. And then that's the speed of light in a vacuum. Well, it turns out when I equate the two, frequency and the 1 over lambda, the proportionality constant that equates these two terms is the speed of light, and it's given a symbol c, lowercase c. So I have the first equation, F equals c times 1 over lambda, which is the frequency wavelength relationship. Well, c is going to be a constant. It's always 3 times 10 to the 8 meters per second. So if you have a wavelength given, and that's a constant, you can calculate the frequency. Or if you're given the frequency with a constant speed of light, you can calculate the wavelength. So this is typically c equals F times lambda in its condensed form. Okay? Now, the relationship of energy is first presented in terms of energy frequency. Now, up here, I showed you earlier that if you have long wavelengths, you have low frequencies. That's a slow vibration. But on the short wavelength end of whatever this diagram is, we have high frequencies or fast vibrations. So as we have a high frequency, we have fast vibrations. So as I go from left to right on this, what happens to the frequency? You start out slow. Now watch me on this. Start out slow, and then as you get further to the end, it gets up higher vibrations. Well, that should lead you to a relationship of energy. So if you have low vibrations, what can you say about the energy that these waves have? It's low, yeah. And as we move up to the higher vibration, high frequencies, what can we say about energy? It's high. So the relationship between energy and frequency is a direct relationship. So delta E is proportional to the frequency, or if you're using the Greek format, you'll see that little V, nu is the Greek letter. But I think that's what's in the Ebbing text, like that. But I like to use the F because it always reminds me of frequency. So I'm going to take that out because I will use frequency like that. Well, our job is to connect the frequency and the energy. Well, it's not connected by the speed of light. There is a unique constant that defines energy and frequency called Planck's constant. And has a value of H, a symbol H. And its value is 6.63 times 10 to the minus 34 joule seconds. Now that will be posted on your reference sheet at the end of the test or whatever we're using. So then this is your proportionality constant that equates this. So when we take these two and combine them, we have the second equation of our wave equations. That's delta E equals h times the frequency. So that's our second. So you're given a frequency times this number gives you the energy in joules. Now frequency units are vibrations per second. That's what's used in your frequency units. But when you put this into a calculation, what you'll have is something like H is in joule seconds, but that frequency will be 1 over seconds. You will not put vibrations up there. You'll just put the time seconds. And when these cancel out, you will get an energy term, joules. See how that works? It's just a manipulation of units. But typically, when we talk about frequency, a vibration is listed as 1 over seconds, or seconds to the -1 is the appropriate way to write it. Now, where we are now is we have this equation, equation 2, and we've derived this equation here, C equals F lambda. Now, what we want to do for the third equation is combine these two into a single equation simultaneously through frequency. See, both the terms have frequency. So if I solve for frequency in this first equation, and then whatever I get, I substitute into the delta E, I will have our third equation, and this is the energy wavelength equation. And so we have delta E equals HF, and we have C equals F lambda, which we solve for frequency, which is C over lambda, and then we substitute that into this equation, and we find the third equation. We have HC over lambda, like that. So to summarize these three, just to put them in one place, you have C equals F lambda that you will need to use. You will have delta E equals Planck's constant times the frequency, and you have an energy equation, HC over lambda. C is 3 times 10 to the 8th meters per second, and Planck's constant 6.63 times 10 to the -34 joules times seconds, like that. So with this, we can calculate various energy characteristics of the light transitions that are in our spectrum. So calculate the frequency of the red band of the hydrogen line spectrum, given the wavelength is 656.2 nanometers. So what we're trying to do is calculate this frequency given the wavelength. So we would use this C equals F lambda, solve for F, and then substitute the speed of light, which will be posted in the problem or in your reference sheet, and whatever the lambda is. Now, one of the points of issue here is the data comes to you typically in nanometers or angstrom. So you'll need to convert this to meters, because the units of the speed of light will be in meters per second, or you can convert this one to nanometers, and that's really not practical. So in this case, the lambda is converted to meters, and that's 10 to the -9th of a meter per nanometer, and that cancels out like that. And so we have 656.2 times 10 to the minus ninth of a meter. And moving the decimal 2 places to the left, we add back 2 decimal places to put it in standard form, and it comes out 10 to the minus 7 meters. Now this is pretty classic type data. When I talk about this kind of problem, this is just one of those, well, this is a classic type of problem and you're going to see it on the test and what have you. So it's to your advantage when you see nanometers, and the problems, all those problems are going to be worked in meters. Just convert to standard form times 10 to the minus 7. It's going to go there. So just be careful in your, if it's one of the bright line spectrums, that is. Now you can get into wavelengths that are far below, very short wavelengths that are below that, and get it, and this won't be 10 to the minus 7 all the time. So be careful about where you're making your conversions. But the color wavelengths will always go to nanometers and meters and 10 to the minus 7 magnitude. Okay, so that's lambda. So all we have to do to get our frequency now is solve this for frequency, and it'd be c over the wavelength, and that's 3 times 10 to the 8th meters per second divided by 6.562 times 10 to the minus 7 meters. Meters will drop out, and your final units will be reciprocal seconds, which refers to cycles per second. Now, 1 cycle per second is also known as a hertz, H-E-R-T-Z. So 4.572 times 10 to the 14th seconds to the minus 1. So you'll see that unit structure in many of the textbooks and published online, and they write out frequency numbers and what have you. But it is simply 1 over seconds and means vibrations per second. Now that's quite a few bounces per second, wouldn't you think? 10 to the 14th. That's more than I can visualize. But all of the light energy has those kind of frequencies. Now, something with that kind of frequency, you calculate the energy, and it has a proportional energy too, HF. So if frequency is 4.572 times 10 to the 14th seconds to the minus 1, and we're going to use that to calculate the energy, and you recall energy is H times frequency, and H is 6.63 times 10 to the minus 34 joule seconds times the frequency of 4.572 times 10 to the 14th seconds to the minus 1. Well, the seconds to the minus 1 will cancel with the seconds in the Planck's constant. Like that, you're left only with joules. So our problem reduces to just multiplying those two numbers together. And we get 3.03 times 10 to the minus 19th joules energy of red line. Okay. Now, you can also calculate this energy given wavelength. Now, this is the equation between energy and frequency. But remember, delta E equals hc over the wavelength, inversely proportional, longer wavelength, lower energy. So given the wavelength of the red light, wherever it was here, it has to be in meters. You can do the same number, 6.63 times 10 to the minus 34 joule seconds, 3 times 10 to the 8th meters per second divided by the wavelength expressed in meters. And we'll also get the same energy number that way. So you have two equations that you need to be aware of. Now I gave you a handout last time that has some simple problems on it. They give you frequency and calculate energy or calculate wavelengths from given frequencies and so forth. But the simplicity of this is that you only have three equations to deal with. And so that makes it a little bit easier as far as defining what the energy values are and frequencies and wavelengths. Okay, what do we know from the observations? Well, we have this bright line spectrum, which has wavelengths for red, green, blue, and violet. And this gives us these four wavelengths: 656.2 nanometers, 486.1 nanometers, 434.0 nanometers, and 410.0 nanometers. Now these, of course, are your wavelengths. Now, calculating the energy for each one of these, we came up with 3.03 times 10 to the minus 19th of a joule for that one. Now, all I did was calculate HC, because those are constants, and divided by each of the wavelengths expressed in meters. And it was move the decimal over times 10 to the minus 7, divide that into Planck's constant times the speed of light. And so it's really very straightforward. But what do you see here in the trend? You see from the red light, as 303 times, everything's in 10 to the minus 19th order, but you have an increasing energy trend like this. So, well, this is the hardest thing for students to grasp, what I'm about to tell you. When we look at the bright line spectrum, we see four specific colors, right? Now, this is where it gets tricky. Now, it's not that complex once you visualize this with me. But we have a red band, a green one, blue one, and a violet, as I've shown you a couple of times already. Now, the unique thing about each of these is they're called discrete wavelengths. That's a very important term. What this means, and I hope you grasp this wavelength, that color, is 656.2 nanometers. Now listen to what I'm about to say. It is not 656.3. It's not 656.1. It's only 656.2. That's a real narrow, no error band, right? This one is, like I was saying, 486.1 nanometers. It ain't 486.2 or 486.0. So what I'm trying to get across to you is these wavelengths are associated with very narrow bands of color. That's number one. Number two, that means that narrow band of color generates a very narrow energy number. So a red band will generate 3.03 times 10 to the minus 19 joule. It will not generate 3.04. It will not generate 3.02. It's a very tight amount of energy. Now, what does that mean in terms of the concentric ring model? Well, if we use this as n equal 2, that's where we're in, of course, one nucleus down on the below us. 3 to 2 transitions, I'm going to put that here. 4 to 2, and 5 to 2. 1, 2, 3, and 6 to 2. So here's n equal 3, n equal 4, n equal 5, and n equal 6. Now, what makes this very unique in defining the concentric ring model is these are also referred to as discrete energy transitions. When we consider what's happening energy-wise, I like to use this relationship. All right, if what I have in my hand, if you watch me for a second, is a pen. Okay, with me holding that pen, it has energy 1. If I throw it up in the air, at the top of its trajectory, it has energy 2. What can you say about the energy at the top of the trajectory as is compared to the energy when I catch it again? Is it higher up there? Higher. Yes. So, but when it comes back down to where I started, what happens? It gives up that energy it gained coming back down. Yes? Well, that's what this is all about here in talking about those transitions. So a transition from 6 down to 2 gives off 4.85 times 10 to the minus 19 joules of energy. Well, that's seen as that purple line and is very discrete thin line. It can't fall above this point or start above it or start below it. It starts on the n equals 6 level and goes all the way to the n equal 2 level. And does not stop anywhere between. And that's true for the blue line, the green line, and the red line transition. This is what makes the idea plausible. The electron is in, say, n equal 3. Then it's n equal 2. It has no existence whatsoever between those levels. No existence whatsoever. It's either in 4 or it's in 2, but not between. It's like you're here and then you disappear and wind up appearing again in n equal 2. It can't live anywhere else. These are called quantum transitions. That's where it comes from. Quanta, because it's a very discrete amount of energy that comes out of there. In the case of the 3 to 2 transition, we have this 3.03 times 10 to the minus 19th of a joule and nothing else. And from the green line, it was 4.09 times 10 to the minus 19th of a joule. The blue line was 4.58 times 10 to the minus 19th joule. And the purple line 4.85 times 10 to the minus 19. So if the electron is living in individual distances away from the nucleus, what does that tell you? That the electrons are orbiting at individual distances around the nucleus. That's how they came to this conclusion, and this is the proof of that existence. Because when they calculated energies, they found, and wavelength, they found they were discrete and so narrow in their existence that you can't say it anywhere else. It starts in 2 and ends on 3. End of discussion. If the electron, here's the catch on the whole thing. If an electron would stop in the middle in here in a discharge tube like I showed you, you'd see the entire continuous spectrum that's on that handout I gave you. You wouldn't see the bright lines. The bright lines only exist because of a discrete transition for each electron as it moves between those. Now there are transitions that jump out and end on 2. That's the UV transition. You can calculate the energies for that one. And then there's transitions that always end on 3, and that's infrared. But we don't see these. Now that's why I use the colors, because at least it means something to you in those transitions. Okay, so this is still in the hypothesis, but it's a strongly suspected, educated guess that the electrons are living at specific distances away from the nucleus. If I start packing everything in, more and more electrons, they will stack up at specific distances away from the nucleus. You'll fill up the first energy level, and the second one, the third one, and the fourth one, and that's how they drew these things in the end. Now, what they needed to do to prove the finality of this is to show that they could calculate they could prove that if I take an electron in the fourth energy level and an electron in the second energy level, that it would give me a certain energy transition and a certain color, independent of those wave equations. And this is how they got that. Let me show you this. These are called the Rydberg equations. And yes, they're very important for your exam, because these confirm the concentric ring transitions, or the electron transitions that are happening within the atomic structure. When an electron is in a given energy level, say n equal, we'll take 2, n equal 3, and n equal 4. The potential energy is given by minus a over n squared. The potential energy in another level is given by en equals minus a over whatever that one is. So this is the fourth energy level, and this is the second energy level. N equals 2, n equals 4. And if I take the difference in those two, I should get the delta E that matches a 4 to 2 transition. This is a very simple. A is 2.18 times 10 to the minus 18th of a joule. That's the constant. It's posted on the reference sheet. So if we have the, this is a positional energy now. Now, positional energy means my electron's laying right there, like sitting on a shelf. And then it's going to transition down to here, and it's going to be sitting on the shelf number 2. The potential energy on the fourth level is higher than the potential energy on the second level, and you'll see that. So En equal 4 is equal to a minus 2.18 times 10, and it's negative because it's exothermic as it moves toward the nucleus. Minus 18th of a joule divided by 4 squared. And then En equal 2 is equal to a minus 2.18 times 10 to the minus 18th of a joule over 2 squared. So let's see what those numbers look like. I get 1.3625 times 10 to the minus 19th of a joule. That's its potential energy. And this one's 5.45 times 10 to the minus 19th of a joule. So I want the delta E for the 4 to 2 transition. Of course, that would be second minus the first. That'd be E2 minus the E4. Yeah, actually, that's negative. So delta E for N equal 4 to 2 is energy while it's living in 2 minus energy while it's living in level 4. And so that works out to be the difference in these two. Energy 2 is a minus 5.45 times 10 to the minus 19th of a joule minus a minus 1.363. I'll stop there. I'll just stop it at 2 digits times 10 to the minus 19 of joule. And so let's see what our transition looks like. 19 plus, let's see, negative plus 1.36 times 10 to the minus 19, missing one. I got 4.09, should be 3.03. Okay, so what was this calculated from? Well, we calculated this energy number using the delta E equals HF. That's the wave equation. So since this matches just simply the transition 4 to 2 calculation based on potential energies, then it is confirmed that the electrons live in discrete energy levels and can only live in discrete energy levels as they orbit the nucleus, and ultimately it led to the concentric ring model. So given X electrons, you place them into the atom, building up with respect to maxing 2n squared electrons as you put them in the orbitals. So if you have a nucleus and you got 10 electrons, well, I've got room for 2 here and 8 here. So I'm going to put the first 2 here, and then I'm going to put 8 here. So 8 and 2 is 10 electrons. So that's the way the concentric ring model evolved into what we know it is in the history of this concept. Now, this differential, there's 2 equations that you have to deal with in this differential of energies, potential energies. One is the energy equation. All I did was take delta E and take the E final minus E initial. Everybody understands that, I hope. You can take that. But the positional energies for each one of these was minus A over N squared in final minus A over N squared initial. And I simplified that into an equation known as the Rydberg energy equation. Now you can go into the book and you can see how this is manipulated, but it works out to delta E equals, and go with me, A onto 1 over N squared initial. Trust me on this for just a second. N squared initial minus 1 over N squared final. See, minus times a minus is a plus, so this term on the end of this calculation is switched with the first one. And that's why it came out initial final like that. But this allows you to calculate the energy, and that's equal to hc over lambda for any given wavelength right here. So you could use this to calculate the wavelength based on a transition. What's the 9 to 1 transition? Well, we haven't invented 9 rings, but you can calculate it. Anyway, this simplifies by calculating for the lambda calculation. It's called the Rydberg wave equation. We're fixing to stop, take a break, hang on. So I solve this term, these two terms on the right. I divide both sides by h over c, hc over here, and I get an equation 1 over lambda to equal a over hc 1 over n squared initial minus 1 over n squared final, like that. This term is all constants. You can see the energy constant A, Rydberg constant, and speed of light. So that comes out to what we call the Rydberg constant. And I'll summarize all these little equations for you. And it's given the value of R. Some people put RH because it's based on the hydrogen. And so this becomes 1 over lambda to equal RH, 1 over n squared minus 1 over n squared initial final. And there's your wave equation. And there's your energy equation. Now, let me summarize all the equations for you that you will need. And you will have problems on each one of these come exam day. So we have C equals F lambda. We have delta E equals HF. Delta E equals HC over lambda, like that. Now these are just a classic wave calculation equation. But what Bohr and his group derived were the Rydberg equations, and that's delta E is equal to A onto 1 over n squared minus 1 over n squared, and it starts with initial and goes to final because of the derivation. And then you have the wave equation, the Rydberg wave equation, which is RH onto 1 over n squared initial minus 1 over n squared final. Now these are not difficult to apply. In the wave equations, classic wave equations, you're given 2 or 3 of the 4 terms, and you just simply solve for the others. The trick is be sure to convert your wavelengths and frequencies to the appropriate units. That's the trick. Over here you choose a transition. What is the wavelength of a 6-to-1 transition? I don't know what will pop up on the exam, but you just simply plug it in. Of course, A is 2.18 times 10 to the minus 18th of a joule, and the Rydberg hydrogen constants 109,678 centimeters to the -1. I just remember because I've done it for 40 years. At any rate, these are published on your reference sheet, so you don't have to go trying to memorize stuff you'd look up anyway.